So we want to consider, let us consider the titration of let's make the 50 a little bit more clear than this, of 50.0 milliliters of a 0.10 molar acetic acid solution, which if you remember we abbreviated as HAC, because I don't like writing out all the C's, O's, and H's. It hurts my eyes. It's too many atoms floating around. And we're going to titrate it with a 0.10 molar NaOH. So our titrant is the same as before. It is a strong base, sodium hydroxide, but this time we're titrating a weak acid, not a strong acid. Now, because we're dealing with a weak acid, you can pretty much guarantee that the Ka is going to show up somewhere. The Ka of acetic acid is 1.8 times 10 to the negative 5. Okay, so let's go ahead and get started. So the first thing we want to do is we want to calculate the pH of the solution before any NaOH is added. So no NaOH added yet. Well, you know how to do this. This is a typical weak acid problem. There's no NaOH has been added. You basically have 50 milliliters. You have a solution as 0.1 molar acetic acid. How do we calculate the pH? Well, we're going to do an ice chart. So this is a typical weak acid problem, which I guess is probably pretty good. I'm going to do a little bit of quick review here. So let's see what our major species are in solution. You will definitely want to get into the habit of doing this as a conditioned response. Any kind of aqueous chemistry, you need to find out what's actually in that solution to decide what chemistry is going to take place. So our major species are going to be HAC, our acetic acid, which is a weak acid, which is why it shows up as the non-dissociated form. And we have H2O. That's it. Those are the only things floating around in solution. Well, between the two, 1.0 times 10 to the negative 14 is the Ka of water. HAC, it has a Ka of 1.8 times 10 to the negative 5. It's going to dominate the equilibrium. So the equilibrium that's going to take place here, as you drop it into solution, what's going to happen? What's going to happen is the following. The HAC, standard acid dissociation equilibrium, H plus AC minus. It's always the same. The acid loses a proton for its conjugate base. Always the same. We have an initial, we have a change, we have an equilibrium. When we're dealing with equilibrium issues, remember ice is for equilibrium, we deal in concentrations. So the concentration of HAC is 0.10 molar. There is no this and there is none of that. Some of this is going to disappear, so this is going to show up, and this is going to show up, the amount that disappeared, right? So we get 0.10 minus x, we have x, and we have x. Okay, let's go ahead and do it. I'm actually going to do it over here off to the side, I think. The Ka is 1.8 times 10 to the negative 5. It is equal to the hydrogen ion concentration, which is x, times the acetate concentration, which is x, all over 0.10 minus x, which is the HAC concentration. Well, this is approximately equal to x squared over 0.10 because x is going to be pretty small. It's going to be pretty small because it's very little dissociation. And you can check it with a 5% rule if you want, but you can take my word for it. And we get x equals, the H plus concentration is going to equal 1.34 times 10 to the negative 1, 2, looks like 3, which implies that our pH is going to be 2.87. So we're going to start off with this pH of 2.87 before any base has been added to this solution. Okay.